in an unconditional strong way, because this acts like a one-time pad to the message. So you cannot see who sent what. But when you add all the messages up, you see that we have once the positive and the negative element of this key once there, and so these two will go away, these two will go away, and these two will go away. And what is at the end on what we have at the end is the sum of all the three messages without knowing who sent what in the whole scheme. So, and this is afterwards actually what we want, but this is first the cryptographic primitive which was introduced by David Chaum. So, and now we come to the protocol. The protocol has several phases. We start with some poll initialization, which is similar to this initialization at a Doodle server. So you go to some web page and say, okay, I have some time slots and some voters. In difference to Doodle, you have to specify the voters, so which is afterwards your anonymity set of the people who will participate in this poll. And you or the server will send an email to everybody, hey, this is the link to our poll, and these are the time slots where we want to schedule some meeting, and these are the other participants. So afterwards, everybody exchanges some key. And when we look into this key exchange, it looks quite similar to what we have seen now. So Alice and Bob exchanges the key, where Bob stores the negative inverse element of this key, but we have not only a key, but we have a key vector, which is not one number, but we have several numbers. So, and we have one number for every time slot we exchanged, or we configured in the initialization phase. So after exchanging the keys, everybody sends his encrypted vote to the server, and this encrypted vote looks like this. So it's a vote vector where is one encrypted vote for every time slot, and in for every time slot we take our actual vote and encrypt this with the keys we have exchanged from the others. So this actual vote is an element, of course, an element of the group we calculate, but it is defined to be only valid when it's 0 or it's 1. So 0 means I cannot participate at this time slot, and 1 means I can participate. So after everybody voted, the server sends us an email notification with the missing vote vectors we also need, and from this we can calculate the result of the vote, because we now can build up such a matrix where all the vote vectors are on the matrix, and when we look at one column, we see that we have here the vote we encrypted, the first thing. The second thing is the vote Bob encrypted, and here's Carol's vote. And again, we see that here is every vote vector, every key, once in the positive form and once in the negative form. And when we add all the three vote vectors together, the keys will go away, and what we get is the sum of this column. And this is actually what we want to have, and we get the sum from this without knowing who voted for what. So, and when we do this for every column, we choose the time slot with the highest sum, and we are ready. So, really ready? No, we can try to cheat. Who has something where we can cheat? Who can see something in this protocol? So we have this, so the Web 2.0 programmers of you should scream, no, there is some user input, and user input is every time bad. Because what the voter can do is just send something different than 0 or 1. I said it's an element of the group, and we have to calculate in some group. We cannot take only a binary number here, because for this calculation and for the calculation later on, we need a group which has the modulo which is higher than the number of participants in our vote. So if we have 10 participants, we need at least the modulo, calculate here modulo 10 or modulo 11, and therefore you can choose here any element from 0 to 9.
But maybe it's okay to have maybe 0.7. So I say, oh yeah, it's pretty good that I will attend, but I'm not really sure. So it's like 0.7. And so maybe it's a feature.
Yes, okay. We can think about this later if we can try to do this as a feature, but yes, this would be really a problem, because what means when sending here, so we can use instantiate two values, so we can send a -1 and a 2 here. And what is the meaning of a -1 here? If we have modulo 11, the -1 is 10. So then you have to say something like, okay, you can say from 0 to 5 or from 0 to -5, and the cheater can always say the most negative value and then cheat the others that every time comes 0 and these things. So yes, you have to be really careful, and we have to look at this, what happens here.
You need some range checking before doing this.
Yes, we need some checking, but the problem is we encrypt the vote afterwards in an information theoretically secure manner. So we cannot have a verification with this encrypted vote. So, okay, everything okay until here, or are there more questions for the understanding? So then, remark that I only have to look at this vote, and we do not have to look at if we cheat with these keys, which are user input as well, because cheating with a key would be the same as cheating with a vote, so we can add these to the others. Okay, so we want to investigate two things. The one is I send a -1, and the next thing is I send a +2, because if we have looked at these two cases, we have every other case where which is then only an extension of this case. So the first thing is we want to avoid -1 cheaters. I have here a table where only the clear votes are written, and we see we have this vote where Alice voted 1100, and we have the sum at the bottom. So in this case, we would choose this second time slot, for example. But maybe Mallory doesn't want to take the second time slot because there she's not available, but she wants to have the third time slot, which would be much better for her. So what can she do? The first thing is, I said, she can send just a -1 there. So, but what happened now? When she sends a -1 on every other time slot, on the last time slot, a -1 occurred. So, and this is, of course, you will see this in the output because the sum cannot be a -1. So it's only valid if it's in the range from 0 to the number of voters. And one other thing would occur here, the 0 would be detected too because Alice knows she sent a 1. So, and if she sent a 1, for her here, the range should be 1 to the number of voters. So, but yes, we can argue with a little knowledge about the things of the other. Mallory can guess when the others are available and send only a -1 here, and she would win and the 2 is there. So with this little knowledge. But what we've seen now is the problem for Mallory was she has to guess where the others sent a 1. So, and we can try to make this harder for Mallory in a way that everybody distributes his vote vector into several tables so that Alice says, okay, I want to send a 1100. We take 3 tables at the end, where I send in the first all zeros, here this one and here's this one, and in the sum I get my vote from Alice. So Bob is doing the same, so he has here a 1, here a 1, and here all zeros. And what we achieved with this is we just made many zeros, which are really randomly distributed along many tables. So think of 100 tables here. So, and we can ask ourselves, the sum of every table should be higher than 0. And for the calculation for our time slot, we only take the sum over all tables, which you can calculate. So this makes it really hard for Mallory because she knows what values she can send here, but this value she does not know. She has to guess where she will send a -1, and this is 1/3 here in this example, and this, of course, has to be a bit higher then. So, and with this trick, we can avoid the -1 cheaters. It's okay? So yes, but we said, okay, there's another way to cheat. Here, for example, she can send a 2 at this day. So, and what